Okay, now this topic 4.4 will be looking at reactor analysis. So earlier on, we have actually described three types of reactor: one batch reactor, CSTR, and one PFR. So over here, we're going to look at how we analyze each of these reactor. Okay, for any reactor system, the material balance in terms of mole is written as input plus generation minus output minus consumption equals accumulation. So this general equation can actually be applied for the three reactor: batch, CSTR, and PFR. So we will look at one by one first. First of all, we look at batch reactor. So remember, initially we say that batch reactor, there's no input or output during the progress of the reaction. So all the material are charged inside, react, and then discharge. So if now what we do is we use this general equation and do the analysis. We begin with input plus generation. As the name implies, generation will cause the reactor to have more and more A. So that's why this is a plus term. And output will reduce the concentration or the amount of A or any species that we are concerning. Minus consumption is equals to accumulation. Okay, all this is in terms of mole. So for a batch reactor, there will not be any input because we say already all the material are charged inside. Okay, there will not be any output as well. And then if we have a generation and consumption. We are more interested in looking at consumption, so there will not be any generation. So all we left with negative consumption will be equals to accumulation. Okay, so for a species A, this is the material balance. So the rate of, now we look at all this in terms of mole. So accumulation is expressed as dNA dt. Okay, and if we want to express this in terms of fractional conversion, where Na is Na naught 1 minus Xa. Okay, so we sub this inside, you're going to get Na naught 1 minus Xa dt. And over here, what we do, we can expand it dt, and we can split the differential term. So Na naught is always a constant because the initial amount of mole will not change because that's the initial amount that we put in. So this is 0. And now we will have this term. Na naught, since a constant, we can bring out the differential term. So negative Na naught is dxa dt. Okay, this is for accumulation. Now we look at the consumption. Consumption of A is written as minus RA. That's what we always say. But now we are looking at the per unit mole basis, and RA is most of the time in concentration, so we need to multiply by the volume V. So this is the consumption term, this is accumulation term. And initially we say that the negative consumption, based on here, negative consumption equals to accumulation. So consumption is minus RAV. That is the negative of consumption. And equals to accumulation, which is NA naught dXA dt. So we can cancel off the negative sign, and we will have this NA naught dXA this is T. T is minus RAV. So we do this separating the variable. We put the T on one side from T to 0, and now we put the rest on the other side. NA naught is a constant, so we can leave it outside the integral, and you get dxa 1 over negative RAV. Okay, you'll get xa and 0. Remember, at time equals to 0, xa is 0 because xa is conversion. So when time equals 0, there will be no conversion. But when time equals to t, xa will then be equals to the xa that we are looking at. Okay, and do take note over here that this negative sign should not cancel off the negative sign here. This negative sign here is to state that the A is being consumed. So we have come to this term. And if we do the integration on this side, it will just give you a value of t. And this will have a NA naught xa over 0 dxa over negative RAV. So this is a generic equation because we didn't consider that V is a constant, because if let's say we are dealing with gas phase reaction, V is not constant. In a non-constant density environment, V is not constant, so we didn't bring it out. But what if the density is constant? Then we can bring out the V. So T will be NA naught V xa and 0 1 over negative RA dxa. Okay, and NA naught over V will be Ca naught. Okay, this is one of the equations that we commonly use. Okay, so this I must emphasize again. This equation can only be used if we are dealing with a constant density system or batch reactor, constant density batch reactor. Alright. Okay, so we based on the definition of conversion, we can write that Na is Na naught 1 minus Xa. And if we divide throughout by volume, then Na over V will give you Ca because it's concentration term. Na naught over V will give you Ca naught 1 minus Xa. Okay. So 1 minus Xa is Ca over Ca naught. And we will take the differentiation on both sides. Differential and this is equivalent to like we differentiate 1 minus differentiate Xa. So differentiate 1 will give you 0, differentiate Xa will just negative dxa. because this is not 1 because we didn't state that we differentiate with respect to what. So this is dxa. And Ca naught is a constant, so we can bring it out 1 over Ca naught dCa. So we have this term over here. And if you make dCa the subject, will be Ca naught dxa. And of course, we're not forgetting the negative sign. Okay, there's another way of arriving at these terms if you don't feel that this process is comfortable. What we can do is we get from here Ca is Ca naught 1 minus xa. So we expand it Ca naught minus Ca naught xa dCa. Then now we differentiate with respect to xa, dCa dxa. It's just like your dy dx. So Ca naught is a constant, this will be 0, minus, because this Ca naught again is a constant, we rewrite it. And if you differentiate xa, you'll give you 1. Because now we are differentiating with respect to xa, so this will give you 1. So all in all, we'll get a negative Ca naught if we differentiate it. And with this, we make dCa the subject, Ca naught dxa, and of course not forgetting the negative term. So from this way, we also show that we can get the same relationship. So depending on which one you feel more comfortable in. So with this, we sub into the previous equation of T is Ca naught xa 0 dxa over minus Ra. We're going to sub this inside here. Okay, this is a constant density batch reactor. What we do is we're going to bring it the Ca naught inside. Okay, once we bring this Ca naught dxa inside, we can see that it's become negative dCa. Okay, and of course at this moment we should not be writing xa and 0. This should be written as Ca naught negative dCa over R minus Ra. This is the integrated rate law that we have seen in our batch reactor. Remember that when we do our batch reactor in the previous chapter, topic 3, that is how we arrived at T is okay. This is what we have seen in our integrated rate law. Okay, with this we're going to move on to look at the example 4.2. The following elementary reaction take place in a batch reactor given that the concentration of Ca0 is 0.5 mole per liter. The reaction rate constant K is 0.125 per minute. So write the rate of disappearance of A. So rate of disappearance is negative Ra. So minus Ra, this is our rate law, is Kca. So how do we know that it's a first order? because it states that it's an elementary reaction for A. So this is the rate of disappearance of A. So B, determine the concentration of A in the reactor Ca after 15 minutes of reaction time. So we're going to use back our equation where T is integrate of Ca naught 1 minus Ra dCa. The equation that we just derived for a constant density batch reactor. So what we do is we sub in the minus Ra with Kca dCa, and this is T. So we put the term K is a constant, so we can bring it out. So it will be Kt integrate of 1 over Ca dCa, Ca over Ca naught. And because this is a first order term, so you will have a ln Ca minus ln Ca naught. Okay, I put the negative on the K over here. So this will be ln Ca over Ca naught, which is your minus Kt, and Kt will be ln Ca naught over Ca. So why there's a change? Because I bring the negative sign to the right side, and this is the power minus 1. That's why that we get this. It's just a revision that we have explained before. So you look at this, is very familiar that we've seen before, and explain how come in topic 3 we are looking at this kind of equation, that how we achieve this integral or this differential equation. And this is our integrated rate law for first order that we are now very familiar. So now we're going to solve this question that K is 0.125 per minute, and T for this case is 15 minutes, and ln, we are looking at concentration of A. Ca naught is 0.5 and Ca. So we're going to work out the left hand side first. You're going to get 1.875 ln 0.5 over Ca. So 0.5 over Ca is e to the power of 1.875. That will give you a value of 6.521. And we work out the value of Ca. You should get a value of around 0.0767 mole per liter.